Good morning. In the last class, we looked at binary trees and we looked at two applications. One is constructing of a Huffman code using binary trees, and we also talked about the construction of an expression tree from a postfix expression using both binary trees and stacks. Today, and then I talked about the different types of traversals of a binary tree, and we saw that when we take the expression tree and traverse it in order, we got the infix expression, and when we traversed it post order, we got the postfix expression, and pre order we did not do, but you will get the prefix expression. So, today what I am going to talk about is I am going to, and so just to recap, what is pre order traversal? Pre order traversal is visit the root and visit the left child in pre order recursively, and then visit the right child in pre order recursively. In order is visit the left child in order recursively, then visit the root, then visit the right child in order recursively. Now, and what is post order? Visit left child in post order recursively, visit right child in post order recursively, visit root. Okay? And post order is what gives you your postfix expression. Now, what we will do is, suppose now we are given the traversal of the trees. Given the traversal of the trees, can we construct a unique tree? So, here we have a binary tree which is given to you, and let me go through this example for you. So, what do we have? We have A here, B, C, D, E, F and G and H, some arbitrary binary tree. Okay? That is, what is it that I am assuming? I have a given binary tree like this, and given this binary tree, we want to construct its, determine its pre order and post order traversals. Okay, let us look at the pre order traversal. What a pre order traversal tell me? Visit root, then visit left child and right child recursively. That means, what am I going to do? I am going to do the left child first, then find B, then this has to be done recursively. Remember, in any recursion, what do we have to do? You have to go down till the recursion terminates, and only then you can backtrack. So, I visit B, then I go down, this is the next node which I will display, and DG, then we will come back, because this left subtree is completely over now. Remember, we started with A, we came down to B, we came down to D, this has no child. Okay. Therefore, we then look at the right subtree. Okay. Then again we go back up, then all the subtrees of D are covered, then we go to the node B, go back one level up, just as it would happen in recursion, and then you look at the right subtree, okay, and it has no other children. Again, this has to be traversed in pre order. Therefore, you do not have, since it has no children, E is the last symbol that will be output, and then what happens? All these nodes have been visited. You go back here and go to the right subtree and visit this in pre order. So, you will get C, F and H. Okay. I think that is what is said over here. So, pre order traversal will give me this. Okay. So, this is pre order. Now, let us look at in order traversal. What is in order traversal? Visit the left child recursively, then root, and then the right child recursively. Okay. So, what happens now? I go down A, I go down to B, visit its left child, left child, left child, because the first node to be displayed will be the left child, then the root, and then the right subtree. So, if I keep going down, what do? I come up till D, D has no left child, then I display the root. So, I display root over here, D, then its right subtree G, then I go back one level up, we have B, then its right subtree E. If, for example, if this one had, then we would have again done this in order. Everything has to be done in order. Okay. Then we go back, then now we display the root A, we come down here again, now you go to the right subtree which has to be again traversed recursively, the in order, recursively in order. So, it goes to its left child, right. So, now this will get displayed because this one has no left child, then it this root F H and C. Okay. This is what will be displayed. F, there is something wrong in that, instead of G there, it should be H over there. Okay. F, H and C. Now, this is the in order traversal. I encourage you to check this. You need at least in order and pre-order or in order and post order to construct a tree uniquely. So, let us look at this particular example and see how we can get this corrected. Okay, what we will do is the following. Now, clearly in the pre-order traversal, the root is the node which is displayed first. So, now I look at this particular root node. Okay. This thing is given wrongly. So, let me go with this only. So, what I will do is, we know that the root node is always displayed first. So, now this must correspond to the root. Then what we do is, we go to the in order traversal, find out where that root node exists. This is where the root node exists. So, what happens in order traversal? The left subtree nodes are before the root and the right subtree nodes are after the root. So, what do we have now? We have now that DGBE correspond to the left subtree and FHC correspond to the right subtree. This is left subtree and this is right subtree. We know this information. So, I go back to the pre-order traversal. So, this corresponds to these 4 nodes. That means, now I have BD, GE and DGBE as the, this is pre-order traversal of left subtree and this is the in order traversal of left subtree. Now, again what do we have? The first node in the pre-order traversal must correspond to the root of the left subtree. So, I mark this. Okay. So, what does this mean now? DG here belongs to the left subtree, E belongs to the right subtree. So, once again I mark this, okay, in the pre-order traversal. Now, what do we have? We are just doing the left subtree now. So, it has DG as the pre-order and we have DG also as the in order traversal. Okay. So, we know that D has to be root, right, and it is in the same order, therefore, this is the root. That means, in the in order traversal, what does it mean? Now, G is part of the right subtree. Therefore, now we can claim what is it that we have done? We had A here, then we had B which was the root of the left subtree, then we had D and G which were part of the left subtree of A. Okay. So, what have we done now? We essentially constructed this part of the tree. Similarly, here what do we have now? If you look at the right subtree of the in order traversal, it is only E and there is only one node, therefore, it has to come over here. So, in much the same way you can go ahead and construct the entire binary tree. And now, you can kind of convince yourself that given the pre-order and in order traversals of a given tree, given binary tree, the tree can be uniquely constructed. Okay. You can convince yourself about this. All right. I would like you to go back and see how you can construct a unique tree from, do this as a homework. From in order and post order. Okay. Now, those of you who are, if you want to be more challenged, can you derive a proof? To show that this proof can be done by construction and using induction, that pre-order and in-order will give you a unique tree. Okay. So, let us next what we will look at is, so we have looked at the binary tree, where binary tree is one where every node has 2 children and both the children are binary trees. It may also optionally have only one child, or it may actually optionally have no children. Even an empty binary, there also exists empty binary trees. This is what we have already seen. Now, what I am going today, what I am going to talk about is, I am going to talk about another type of application of binary trees called the binary search tree. Now, what is a binary search tree? A binary search tree is, it is also a binary tree. It may be empty. If it is not empty, then it satisfies the following properties. Every node, every element or node has a key, and no 2 elements have the same key. What is the meaning of it? That means the keys are all unique. And there is another property, the keys in a non-empty left subtree must be smaller than the key on the root. Okay. The key in a non-empty right subtree must be larger than the key at the root. The left and right subtrees are also binary search trees. Now, let us take an example and see how this will look like. Let us take the same letters of the alphabet. Let us say I have notice that all the keys are unique. Let us say each one of the letters of the alphabet is a key, then this is a binary search tree. Okay. Notice that all nodes on the left subtree have a key which is smaller than the root. I am assuming lexicographic ordering here, and all the nodes on the right subtree have a key which is greater than the root, and that is true of every node. For example, if you take the node B here, left subtree has smaller key values than B, right subtree has larger key values than B, E here again is smaller than G, and right subtree has larger value than the given node. Interestingly, this is also a binary tree. This is also a binary tree. And by the same token, we also have that this is also a binary search tree. Okay. Now, what we will do is, we will look at this subtree. So, basically, why is this also a binary search tree and this is also a binary search tree? By definition, what do we have? A binary search tree has keys that are unique, no doubt about it, all the keys are unique. And what did we say? Elements on the left subtree, it can, binary search tree can also be empty, and elements of the left subtree should be smaller than the root, which is smaller than the elements on the right subtree. And this is true for this tree, and it is also true for this tree. These two trees are what we call skewed binary search trees. What is the application of this binary search tree? For example, you can put the roll numbers in a class in a binary search tree and search for a particular, if you want to find the marks of a particular student, you can find the marks of a particular student using a binary search tree. How would I search now? This corresponds to the root. Suppose I wanted to find out what was the marks that A obtained in this tree, then I give the key and say key is A, go back, let us say there is additional information along with A, I only given the key here, marks and other things are stored over here. I compare A with D, it does not match, then clearly, but A is less than D. So, go down the left subtree, compare with B, A and B again is not match, but A is less than B. Therefore, I go down its left subtree and I find this particular node and I can retrieve all the information corresponding to the given node. This is about searching, the operation of search if I want to perform. Okay. Now, if I want to insert a node, what happens now? Let us say I want to insert F, okay, E, G, H is what I have. Suppose I want to insert the node F. Okay. Then I compare with the root, where should it go now? Compare with the root, then clearly it is not matched, but F is larger than D. So, I go down this subtree, then I compare with G, G and F are again unmatched, but clearly G is larger than F. Therefore, I go down its left subtree, I compare with E, E and F are again not matched, but F is clearly larger than E. Therefore, I go down here and I insert F over here. Okay. Now, suppose I wanted to insert E, can this be done? I compare E with D again starting from the root, clearly E is larger than D, therefore, go down the right subtree. I compare with G, G is larger than E, therefore, I go down its left subtree. I found a match, but since already the binary search tree has a key E, clearly I cannot insert the node E, okay, because the keys in a binary search tree must be unique. Okay. This is a very, very important property. Keys in a binary search tree must be unique. This has to be satisfied. Now, suppose I want to delete the node G. So, what are the operations? We are looking at search, we are looking at insertion, we are looking at deletion. This is also common, right? A student leaves a program and you want to delete the particular name from the list. Okay. Suppose you want to delete the particular node G, then what should I replace it? I should replace it with some node such that the binary search tree property is not satisfied. We can do one of two things. We can replace, suppose I want to delete G, I can replace G with either the largest node on the left subtree or the smallest node on the right subtree. Why do we do that? Because then we can guarantee that the tree will still remain to be a binary search tree. So, this is exactly what we do. So, I put F over here, largest node on the left subtree. So, I find out. So, I go to the rightmost node on the left subtree, find that and put that node over here, delete it. But what might happen is this node might have some left children, but since clearly this in this particular case F did not have any left children, but suppose F had some left children, then what do? I take these left children, make it the right children of E, because that is okay, because all of them have to be larger than this given node. Okay. So, this is the operation of deletion. So, the operations on the binary search tree that we would like to perform are insertion, search, insertion and deletion. Okay. So, these are the three operations that we would like to perform. Okay. Here is one same example. I have done it with numbers in the slide over here to show the operation of insertion. Notice how now let us see how do you get these skewed binary trees. Basically, if I start out with let us look at the insertion over here. Let us say I have been given 8, 5, 7, the keys 8, 7, 8, 5, 7, 4 and 6, 14, let us say 13, 18 and 16. Okay. Suppose these keys are given and we want to insert them into a binary search tree. This will give us an idea why these trees become because we are always inserting it. Just let us go through this example. I have given a partial example in the notes. So, I have 8 here. So, there is initially an empty tree. Okay. So, into the empty tree I insert the node 8. The next I come across the node 5. 5 is smaller than 8. Therefore, I make it the left subtree. Notice that again it is being inserted as the leaf node. Then 7 for example becomes again you compare with 8, 7 smaller than 8, greater than 5, therefore, this has to become the right subtree of this. 4 compare with 8, smaller but smaller than 5, therefore, 4 goes over here. 6 compare with 8, compare with 5, compare with 7 and then it comes over here, and similarly here compare 14 and 13, 18 and 16. Okay. Always what we have seen is in this process all the nodes simply get inserted at the leaf node at every stage. Now, suppose instead of giving this sequence I had given you this sequence 1, 2, 3, 4, 5. Then initially there is an empty tree, I insert 1, then I insert 2 because the right is larger than this, then 3, then 4 and then 5. So, this is how a binary search tree can become very skewed. So, let us do some analysis of the complexity of this binary search tree. What is the cost of search now? How expensive can search be? Okay. So, clearly in the worst case what is it going to be? I may have to traverse down the height of the tree. Now, what is the height of the tree now? Basically you compute the path from length of the path from root to the leaf node 1, 2, 3. Okay. All right. So, the worst that you have to do, suppose I want to compare with 6, if the key that I am searching for is 6, therefore, the complexity becomes the height of this tree is 1, 2, 3, but I have to make 1, 2, 3, 4 order height plus 1. So, I have introduced a new concept today, the height of the tree. Okay. So, the height of the tree is the number of comparisons plus 1 is the maximum number of comparisons that you may have to perform if you want to search for a given node. And this is also true for deletion, right, because if I want to delete or insert for example, I have to come down and then move back up in deletion, whereas in insertion again insertion happens at the leaf, therefore, I have to go down to the height of the tree. What can the height be in the worst case? Height, what can it be in the worst case? The worst case. What can it be in the worst case? In the worst case what can happen is you can have a completely skewed tree and the height can be n minus 1. If n is the number of nodes in the tree, then the height of the binary search tree can be as tall as n minus 1. Okay. So, when you are talking about order of h plus 1 comparisons, in the worst case you have to do order n comparisons in the binary search tree. So, this kind of completes the and I have just let me give you a small implementation of insertion. Here is a small segment of C code, C code sorry, which is given here. So, let us say that you have a pointer to tree as we had in the Huffman tree. So, what we are doing over here is, if tree is equal to null, then what are we doing? We are creating a new symbol. In this particular case, I am assuming a binary search tree which only has numbers. Otherwise, what am I doing? I am comparing if it is not an empty tree, I compare with tree symbol, and then what do? We insert it. If it is if it is smaller, then you go to the left subtree and then do the insertion again. Insertion is called recursively over here. Okay. Similarly, otherwise, if letter is greater than the given node, then what are we doing? We are inserting in the right subtree. Notice that we are not doing anything if the symbol is already present in the tree. Okay. So, this is a very important point in binary search trees. Okay. All right. So, this is something that is a small segment of code over here, a recursive implementation of the insertion into a binary search tree. All right. Okay. There should be a correction here. This letter should read number. Please correct this. It's else if number less than tree symbol, number greater than tree symbol. Okay. So, this is about binary search trees.